Hello everyone, welcome back. In previous lecture, I explained about the geometry of single point cutting tool. Now, in today's lecture, I will furthermore discuss about the different cutting tool and their nomenclature. So, the this is the different cutting tool. Here it is, you can see the various parts of the drilling tool, and another is milling tool. So this is not very much important from exam point of view. You can say the single point cutting tool is most timely for exam point of view. I will show you one video where you can actually see the how the various parts of this drill looks like. So uh, here is one video which is showing that the drilling tool. This part is called as the shank portion. Here you can see this is the shank, and this remaining part is called as body. Now apart from that, there is the tip of drill. This point, the tip of drill. Then after tip of drill, you can see over here it is the point angle. Over here this is the point angle, and this one is the drill diameter. The helix angle is the this longitudinal and the flute between the flute. Then this is the recess between this is called as the flute. This gap is called as flute. This point is called as chisel edge, you can see, and the angle is called as chisel edge angle. And apart from this, this is called as margins. Here also you can see the margins, and this portion is known as heel. Heel cannot be visible from here, and this one is the cutting lips. Okay. Also there is one web portion over here. This is called as web. Here you can see, and this portion is called as land. Here you can see the part of cutting tool, and this is called as relief. So these are the various terminologies. This is the diameter of tool. Now the tool is required to be fixed. This is the tool is required to be fixed in the drilling machine. So the tang or the taper shank is provided, and the tang drive is also provided on the other end, so that the tool can fix easily. Now this is the body clearance between tool and this margin portion. There is a small clearance that is called as body clearance, and this is called as the clearance diameter after excluding this body diameter clearance. So this is about the drilling complete geometry of drill. Now let us move on to the next. This is about the geometry of the nomenclature of milling cutter. Now the in milling cutter, this is the cutter diameter, and the angle between this horizontal axis and the inclination of this teeth is called as radial rack angle. As we have seen in the rack angle in the single point cutting tool, same way there is a rack angle. Apart from that, there is a fillet. This recess is called as fillet, and this point is called as cutting edge, and the back portion is called as clearance angle, and this portion is called as relief angle. As we can see that in geometry there is this first line and there is this first angle and there is one another angle. So the first angle is called as the relief angle, while another angle is called as clearance angle. Now this is the nomenclature of milling cutter, and this is the different angles of face milling cutter. There is axial rack angle, and there is insert cutting edge, okay, and there is lead angle, there is a slot for chip, you can see, and there is a wedge section, and there is also radial rack angle, and this one is the insert. So this is about the milling tool cutter geometry. Next, we will be discussing about the cutting force acting in the tool. Now, before that, we have to discuss what are the elements in metal cutting. So here you can see in the single point cutting tool, this is the tool which is cutting, removing the material. Suppose there is a T thickness of chip, okay, input thickness, and this the chip thickness is TC, okay. So as you can see here, the rack angle will be the this from this portion to this portion, the vertical line, and between the tool face is the rack angle. And you can see that the rough surface will be formed over this side and shiny surface will be formed on the tool face side. This is the tool face, and the tool is moving with the v velocity, and this portion is called as flank or relief or clearance angle will be with the this horizontal and flank face. And the phi is called as shear angle, the angle at which the cutting takes place and at the shear plane. Now there are two models for cutting the workpiece. The first one is the tool is orthogonal, which means the tool is perpendicular to the cutting. You can I can explain with the one figure. Suppose the this is the one over here workpiece. Now the tool is the chip will be removed in this direction, okay, and this will be our tool which will be removing material, and this will be exactly at the 90-degree to cutting. There will be no oblique. Here you can see the tool is 90-degree with the workpiece, okay. So the angle over here it is of 90-degree, okay. But here in oblique cutting the tool is in inclined, there is certain angle, it is cutting is taking at some inclination. There are certain advantages of oblique cutting. Here you can see the chip thickness is uniform, okay, but there the chip thickness will be varying, so cutting force required in oblique cutting will be reduced, okay. So the shearing action will be taking place over here, okay. At a time the certain portion of the tool will be coming in contact with the workpiece, and here the in orthogonal cutting the chip thickness will be of same, okay. So there are certain assumptions while in orthogonal cutting model. The cutting edge is a straight line extending perpendicular to direction of motion and is generated generates a plane surface. Here the cutting edge is straight line. Here you can see there is one straight line and extended perpendicular to the direction of motion, and it generates a plane surface, and work moves fast by it, okay. And tool is perfectly sharp and no contact along with the clearance face, while the shearing surface is a plane extending upward from cutting edge. The shearing surface is a plane extending upward. Okay, the chip does not flow to either side. Depth of cut or chip thickness is constant or uniform relative velocity between work and tool. The depth of cut will be constant, okay, and the velocity will be uniform between work and tool, and the continuous chip or no built up edges will be formed. Okay, so these are the certain assumptions in orthogonal cutting model. Now let us see how the turning forces for orthogonal model looks like. Here, this is for the 2D orthogonal mechanics model. We will ignore the radial component only for this. Okay, radial component we will see in the next figure how it will look like. I am showing the separate point for both. So this is our cutting tool and this is the direction of feed. Only the turning action is taking place. Okay. So the force acting will be this longitudinal or thrust force, and this is the velocity of tool relative to the workpiece. That is the v velocity. Okay, and this is the direction of rotation. So the perpendicular force which is supposed to act is called as tangential or cutting force. Okay, Fc, or that is called as tangential force or cutting force. So there are two forces, tangential or cutting force, that is Fc, cutting force, which is acting in this direction. This is the section wave, and here the horizontal force which is supposed to act, that is called as longitudinal. ओके, जो सो यहाँ पे दो फोर्स लगेंगे, सबसे पहला जो है वो कटिंग फोर्स लगेगा और जो दूसरा है वो लॉन्जिट्यूडनल फोर्स लगेगा इन द डायरेक्शन ऑफ फीड, और दैट विल बी कॉल्ड एज thrust, because as the tool moves in this direction the thrust will be applied to this portion while the cutting is taken place by this motion. Okay, जो कटिंग होगा वो ये वाले मोशन की वजह से होगा, यहाँ पे जो टूल है वो रोटेट होगा और उसकी वजह से कटिंग होगा. सो दिस इज कॉल्ड एज एफ सी एंड दिस इज कॉल्ड एज एफ टी. Now the second one is here the facing force for orthogonal model. Same here, you can see the in the facing, the direction of feed for tool is in this radial direction. So there will be the radial force or that will be the thrust force. Here you can see the end view, while the vertical force will be the same. The tangential or cutting force will be same as we have seen in the turning operation. And same way, if we move to the longitudinal direction as well, as there will be longitudinal force. So there are three total number of forces acting in the cutting on the cutting tool. So here you can see the orthogonal cutting tool model, simple 2D mechanist model. The mechanism is here, that the chip produced by the shearing process along the shearing plane. The chip is produced by the shearing process along the shear plane. Here you can see I have earlier explained the TO is the initial depth of cut, or this is the chip thickness before cut, and here TC is chip thickness after cut. This is the rack angle. Rack angle is the vertical, or we can see the transverse versus between the face of tool. जो फेस ऑफ टूल है और जो परपेंडिकुलर है, ठीक है, लाइन, इस इन दोनों के बीच का जो एंगल है दैट इज रैक एंगल. एंड हियर द वेलोसिटी ऑफ टूल इज हियर. दिस इज द shear angle. The angle at which the shearing action takes place is called a shear angle. And here is the clearance angle between the horizontal and flank face. This is the flank face and this is our workpiece. So now this is very much important for deriving various relation or equation. We will see next. Here you can see that the cutting ratio or chip thickness ratio. How to find that the chip thickness ratio? Here you can see this is the phi shear angle. So for phi, and here you can see there is one triangle. Okay, the triangle is forming over here. So this is one triangle is forming, and this triangle, here you can see the sine phi will be this TO by AB. Same way here, there is one another triangle. Let me enlarge over here. This is the, this will look like this another triangle. Here this is same, there is B, and here it is A, and the chip thickness ratio here it is TC. Okay, so the angle over here, it will be the angle between this is the angle, and this one here it is 90 degree. Now the angle will be phi minus alpha, because the vertical angle is alpha over here and this angle is phi. Okay, so what will be the angle over here? This will be the alpha, this one is the uh, phi. Okay, so this one angle will be phi minus alpha. Okay, now the cos phi, if we take the cos component over here, the cos phi will be equal to TC upon AB. Okay, so taking the ratio of both, we can have the TO by TC. Okay, that is called as chip thickness ratio, and it is given by this TO by TC is equal to sine phi upon cos phi minus alpha. Okay, so this is called as chip thickness ratio. And let us move on to the further. There is one another way to determine the cutting ratio or chip thickness, and that is with using the experimental determination of cutting tool. So here what we are supposed to do, we have to measure the every aspect after cutting the before initial chip thickness, which means the depth of cut, and here the TC, the cut chip thickness, width and length is measured of the cut chip. Shear angle phi may be obtained either from the photomicrographs or assuming the volume continuity, no chip density change. Okay, since the volume before and after will be same, so here volume we can find TOWO, and LO is equal to TCWC before cut and after cut. So WO is equal to WC with the experimental evidence. Okay, and the cutting ratio will be TO by TC is equal to LC by LO. So measuring length of chip is easier than thickness. So just by measuring the length of chip, okay, before and after cut, we can find the cutting ratio or chip thickness ratio. Now there is shear plane and shear plane length and angle. So this is the chip and here it is the tool. Now this is the angle. The shear plane will be, shear plane length will be equal to AB, and it is equal to TO by sine phi. So the shear plane angle sine phi, if we want to have that, earlier we have seen the sine upon cos, it was TO by TC. Okay, so it was about the tan phi is equal to r cos alpha upon 1 minus r sin alpha. Okay, so in form of chip thickness, we can ratio, we can find the shear plane angle, which is equal to tan inverse r cos alpha upon 1 minus r sin r sin alpha, or make an assumption such as that the phi adjust to minimum cutting force, and phi is equal to 45 degree plus alpha by 2 minus beta by 2, and this is the merchant. So basically from here you can see the velocity. If we want to find out the velocity from the mass continuity, the velocity v into tu is equal to vc into tc. So vc is equal to v sine phi upon cos alpha minus phi minus alpha, and from velocity diagram vs is equal to v cos alpha upon cos phi minus alpha. So in this particular way we can also find out the velocity. Okay, so with this I end today's lecture. Thank you very much for listening me carefully. Have a nice day.